plus grands géomètres de leur génération. Donc, le premier cette semaine, c'est Simon Brendle. Simon, after finishing his PhD at Tübingen, has been holding academic appointments in various places in North America, including Princeton, Stanford, and latterly Columbia. He's now, of course, a full professor. He's solved a series of very important conjectures in differential geometry, proving convergence of Yamabe flows in all dimensions, the differential sphere theorem, which has shown, the Chiang-Lawson conjecture in minimal surface theory, and a whole broad spectrum of questions in mean curvature flow and Ricci flow. Won a whole bunch of prizes. So the European Mathematical Society Prize, Clay Math Institute Senior Scholarship, Simon's Investigator, the AMS Boucher Prize, and the Fermat Prize, and of course, is given a talk at the International Conference of Mathematicians. So we're very proud to have him here. And I think we'll stop talking and let Simon take over.
Thank you so much for the introduction. And I would like to thank Jacques and Perelman and the other organizers of the thematic program for inviting me to participate. It's a great pleasure to be in this beautiful city and participate in the activities. Yeah, in today's lecture, I want to discuss topics related to geometric evolution equations. And so the basic idea in geometric flows is that we want to start from some geometric object, and then we want to evolve it by a heat equation and deform it to a simpler model geometry. Now, you can do that for various types of geometric objects. So in the simplest case, you can just look at a curve in the plane, and you can evolve it by what's called the curve shortening flow. So you evolve it with a speed given by its curvature. Going to higher dimensions, you can look at a submanifold in some Euclidean space, and you can evolve it with a speed given by its mean curvature. And so the common feature of these two equations is that each of them is a nonlinear heat equation. So that they have smoothing effects because they are heat equations, but there are also nonlinear phenomena that are that make the equations very interesting to study. Now, the third equation on the list, this is the famous Ricci flow invented by Richard Hamilton. And here the object we're considering is a Riemannian metric. And so this last flow, the Ricci flow, this will be the main topic of today's lecture. So before telling you about the Ricci flow, let me first tell you about Riemannian metrics and what we mean by their curvature. Since in the end, we want to look at these objects and we want to evolve them in a way that depends on their curvature. Now, in geometry broadly, you can take an extrinsic point of view and an intrinsic point of view. So if you take an extrinsic point of view, you would look at a submanifold that's embedded, for example, in a high-dimensional Euclidean space. Now here, we want to take the intrinsic point of view, and we want to only look at quantities, geometric quantities that don't depend on the embedding into some ambient space, but that only depend on quantities on the surface. And so the basic object here is a Riemannian metric. And essentially, its purpose is to tell you how to measure lengths of curves for infinitesimally short curves. And then based on that, you can measure lengths of arbitrary curves, and then you can define a notion of distance. So here's how it works. So let's say we take an n-dimensional manifold, which means we have a topological space that's locally homeomorphic to a piece of Euclidean space, and we have transition maps that are smooth. And then we take one such coordinate chart, x1 to xn, and then expressed in these coordinates, the metric is an expression given by a sum Gij of x, dxi, dxj, and this Gij, this is a smooth function that takes values in the positive definite matrices of size n by n. And so what it does is it tells you how to measure lengths of tangent vectors, and then you can compute lengths of curves. For example, if you have a curve alpha of s, then I can look at the velocity vector alpha dot of s, but then because I want a quantity that's independent of the choice of coordinates, I will not take like the Euclidean norm of alpha dot, but I will measure the norm of alpha dot using this metric Gij. So this is positive definite, and then it depends, it changes from point to point, and I use the metric eddy point alpha of s to measure the norm of the velocity vector alpha dot of s. And so in this way, you can use the Riemannian metric to define lengths of curves, and then that allows you to talk about metric distances by looking at the infimum of lengths of curves among all curves joining 2 points. Now, of course, the simplest example of this is if you just take Euclidean space Rn, and in that case, the metric is just the Kronecker delta, and that's the simplest example of a Riemannian metric. Now, let me tell you about the curvature of a Riemannian metric. So if you have one Riemannian metric, you can change coordinates and you get another Riemannian metric that may look very different in coordinate. It's because you passed to a different coordinate system, but geometrically, it's really the same metric. And so in particular, you can have metrics that are equivalent to the standard Euclidean metric up to a change of coordinates, but that don't look Euclidean and in terms of the formula for Gij. So for example, if you look at the metric in polar coordinates, this is still the Euclidean metric. It's just that we look at it in polar coordinates rather than in Cartesian coordinates, but then the metric will no longer be delta J. And so the Riemann curvature tensor, this was designed to tell you whether a given metric Gij is just the Euclidean metric in disguise. That is to say, if you give me a metric, then you can ask the question, well, can I change coordinates to transform that to the delta Ij metric, to the Euclidean one? And Riemann found this tensor with 4 indices that serves as an obstruction to doing that. Now, the complete formula is rather complicated, so let me just tell you the leading order term to give you a feel for what it looks like. So basically, it involves second and first derivatives in the metric. The part involving the second derivatives is linear. The part involving first derivatives is nonlinear, and it's quadratic. And the second derivatives, they enter in this very particular way. And so you can see here that this expression has certain symmetries. So for example, if you switch I and j, it changes sign. And if you switch k and l, it changes sign. And then it has other symmetries as well. So in the end, it's a nonlinear expression involving derivatives of first and second order. And the point of it is that this Rijkl transforms nicely under changes of coordinates. So basically, the nonlinearity of curvature, the fact that it's a nonlinear expression in terms of the metric, that is dictated by the invariance properties you want. So if you wanted to write a linear equation, I mean, you can do that, but it will not be geometrically invariant. And as such, it will not be interesting for geometers. So nonlinearity is just a fact of life. And then because it transforms nicely under changes of coordinates, then if the metric is just the Euclidean metric in disguise, then this Rijkl vanishes identically. And conversely, you can show that if it vanishes on an open set, then at least locally, the metric can be transformed to the Euclidean metric by a change of coordinates. So this is what we mean by the curvature. And it's not that intuitive because it's algebraically fairly complicated, at least in higher dimensions. And so you can now look at simpler curvature quantities that are obtained by contracting indices. Now, there are two reasons for doing that. So one is that they lead to algebraically simpler expressions that are easier to understand. I mean, if you have a bilinear form, a symmetric tensor with two indices, you can diagonalize it, so it's much easier to understand. Also, there's a useful analogy in that you can think of the Riemann curvature tensor as being analogous to the Hessian of a function, and then the Ricci tensor, which I'm going to define for you in a minute, this will be analogous to the Laplacian of a function. And so then it leads to interesting elliptic and parabolic PDEs. Okay, so what is Ricci curvature? So Ricci curvature is a tensor with two indices, and you get it by contracting the second and fourth index in the Riemann curvature tensor. So I contract them with this G upper KL, which is the notation for the inverse of the metric. And so here you sum over K and L, and in that way you get the Ricci curvature.
So the height.
This should work.
Okay, now it's
Likewise.
the height.
Okay, let's go back to scalar curvature. So to get the Ricci curvature, we contract from 4 indices to 2 by contracting the second and fourth one. And then the scalar curvature, this is just a function, and it's the trace of the Ricci curvature. And here we contract the remaining 2 indices. And so by doing these contractions, we lose information, but we get quantities that are easier to handle. And in particular, the quantity minus twice the Ricci tensor, this is analogous to the Laplacian of the metric. Now, there's another reason why this is an important concept, because if you look at this in the context of Lorentzian metrics, then you're in the realm of general relativity, and then the Einstein vacuum equations, they take the form Ricci equal to 0. And so then in the Lorentzian context, you would get a wave equation, but the equation itself would have to do with the Ricci curvature. And so this is Einstein's famous equation in the Lorentzian setting. Now let's go back to the Riemannian setting, and let me tell you what Ricci flow does. So the definition, this goes back to a famous paper by Hamilton back in 1982. And so the setup is you look at a 1-parameter family of such Riemannian metrics. And then we say that these evolve by the Ricci flow if the time derivative of the metric is given by minus twice the Ricci curvature. And so both tensors on the left and the right-hand side, they have the same type. So this is a natural equation you can formulate. So you can think of it as a kind of dynamical system on the space of all Riemannian metrics. Now let me give you a few pictorial solutions. So of course, you can start from a flat metric and then nothing happens. But let's look at something more interesting. And let's look at an object which has positive curvature. And the simplest example is a round sphere, which has constant positive curvature. And then under the Ricci flow, this will contract because you have a minus sign, and it will remain round. And then what will happen is that it will shrink to a point in finite time. So if basically these spheres with shrinking radius, and the radius will become 0 in finite time, at which point the solution ceases to exist. And you can you can do something similar with cylinders. So let's say we have a cylinder, and then we evolve that by the Ricci flow. Then what will happen is that the cross-section will collapse to a point, and the line will not contract at all. So you will keep the line, but the cross-section will shrink and collapse to a point, and then your solution collapses to a line. Now here, I've drawn this picture for a two-dimensional sphere and for a three-dimensional cylinder, but you can do the same in higher dimensions. However, you cannot do that for a one-dimensional sphere, because a one-dimensional sphere has no intrinsic curvature. So if you evolve an S1, it wouldn't contract, but it would just stay the same because it has no intrinsic curvature. And by the same token, if you take a two-dimensional cylinder, S1 cross R, and you contract that, you evolve that by Ricci flow, then again it will stay fixed because S1 crossed with R has no intrinsic curvature. All right, now let me tell you about other examples, which are less symmetric. So one is what's called the cigar soliton in R2. And this is a very simple closed form expression. You take the Euclidean metric and then you multiply it by a scalar function. That's called a conformal deformation because it doesn't change angles. It just stretches distances at every point by a factor that may vary from point to point. And then the factor is very simple. It's 1 over 1 plus x1 squared plus x2 squared. And if you look at this metric, if you try to picture that, it will be rotationally symmetric and it will open up and be asymptotic to a cylinder because the cross-sectional radius, this will approach a constant. So if I didn't include the 1 in the denominator, then that metric would give you exactly a cylinder. And so with the 1, you get kind of something that's asymptotic to a cylinder. Now this metric, this has a very special property, namely, if you evolve it by the Ricci flow, then the metric at any time t is a reparametrization of the original metric. So in a certain sense, this is a fixed point of Ricci flow. But so the metric itself changes because this metric is not flat. In fact, it has positive curvature. So the metric itself changes, but it changes in a very simple way in that the metric only changes by reparametrization. So all the essential geometric features, they don't change. And so a solution with that property, that's called a self-similar solution or a soliton. Now you can do play the same game in higher dimensions. And it turns out that in 3D and in any higher dimension, there's another self-similar solution which has rotational symmetry and which also has positive curvature, but it looks rather different. While the 2D cigar soliton opens up like a cylinder and the cross-sectional radius approaches a constant, the 3D analog, which was found by Robert Bryant, this is asymptotic to a paraboloid. So if you go out a distance s, then the cross-sectional radius will grow asymptotically at a rate of square root of s. And so this keeps on opening up. And I will not have time to explain why there's this difference, but in short, the difference has to do with the fact that the S1 has no curvature from an intrinsic point of view, but the S2 does. And so for that reason, the asymptotic behavior is different. Okay, so I told you about some special solutions. Now let me go back to the general properties of Ricci flow. So one of the central features of Ricci flow is that it behaves like a heat equation. And you can make that precise in various ways. So one way to see it is by looking at the evolution of curvature. So under the Ricci flow, the metric keeps on changing as time evolves. And so then the curvature is a function of the metric, so that will evolve as well. And so then you can ask, how does the curvature change over time? And the evolution of curvature, this is governed by a PDE, and it has this fairly simple form where the time derivative of curvature is given by the Laplacian of curvature plus a term q, and this is a quadratic polynomial. And so this looks like a reaction diffusion equation, but there are a couple of points to mention here. So first of all, you're dealing with a system, actually a very large system, because like I, j, k, and l all run from 1 to n. So you have roughly n to the 4 components of curvature. In fact, you have less than that because of symmetries, but nevertheless, in large dimension, this becomes a very complicated system. As a result of that, this Q of R is algebraically rather complicated. So even though it's a quadratic expression, a quadratic polynomial in many variables can become complicated. And the polynomial, this is related to the structure of the Lie algebra of little SON, but I will not have time to go into that. The final point is that the Laplacian, this is not a fixed Laplacian, but this is the Laplacian with respect to the time-varying metric. So the diffusion coefficients change over time, which makes sense given that the metric changes over time. And the metric really is the diffusion matrix of that PDE. All right, nevertheless, given that this is a parabolic equation, you expect to get short time existence. And indeed, this was proved by Hamilton back in 1982. So he showed that if you start from any compact manifold and any initial metric G0, no assumptions whatsoever, then you can always solve the Ricci flow for a short time. And you can extend it to some maximal interval, which always has positive length. And then there's a dichotomy. So either you can say, you can solve the equation forever, then this lifespan capital T is infinite, or the other possibility is that the lifespan is finite. And in that case, the curvature must be unbounded as you approach the end of the lifespan of the solution, as you send T to capital T. Now, the main goal in studying Ricci flow is to understand singularity formation. Specifically, suppose that we have a finite time singularity, then what happens as the curvature blows up? Now, an interesting point here is that here the point of view is different from many other problems in PDE theory. So many times in PDE, the ideal result is a result that says that you get a global solution and you get a priori estimates. Now in Ricci flow, this is A, not feasible, and B, not desirable. First of all, it's not feasible because even if we go back to the simple example of the shrinking spheres, we get a finite time singularity and the curvature blows up. So blow up of curvature is unavoidable. And I mean, it happens in the most basic examples. The second point I want to make is that you can say a lot more about a solution when it blows up than when it stays smooth. So when it stays smooth, well, you have a solution, but other than the fact that it exists, there's not all that much you can say about it. On the other hand, if the curvature blows up, then it turns out that the curvature can only blow up and the solution can only become singular in very specific ways. And so the fact that it blows up gives you very specific information about how it can blow up. And most of the interesting results about Ricci flow happen in this regime, in the large curvature regime. So this is something to be embraced rather than something to be avoided. Okay, so let me give you a couple of examples of that point of view, which relates to some of the classical successes of Ricci flow. So let me begin not with the chronologically first result, but with the one in lowest dimension. So let's say we're in 2D. And so in this case, if you start, let's say you start with any metric on S2, then it turns out that the Ricci flow has a certain time interval on which it will exist. The length is proportional to the area of the manifold at time 0. And then as t approaches capital T, the manifold collapses to a point and it becomes round after rescaling. So that you have these two things going on. It collapses to a point, but if you look at it under the microscope, then it will be round. So the curvature gets kind of dissipated. It gets distributed uniformly across the manifold. Now, this can be used to give an alternative proof using Ricci of the uniformization theorem. So at least in 2D, the picture is very simple, and you always get convergence to a constant curvature metric after rescaling. Now, going up to dimension 3, there's this landmark result by Hamilton, where he considered a 3-manifold and a metric with positive Ricci curvature on that 3-manifold. And so then what happens in that case is, again, the solution exists up to some finite time capital T, but you can no longer compute it easily in terms of the initial data. As you approach the time capital T, the solution collapses to a point and it becomes round after rescaling. So this gives you a kind of a uniformization theorem for 3-manifolds with positive Ricci curvature. So then you can, based on the fact that you can find a constant curvature metric, you can understand the topology. But of course, this is under the assumption of positive Ricci curvature. Now, there are two directions you can go from here. You can either go to higher dimensions and impose some positivity condition on curvature and try to prove a similar convergence result in higher dimensions. The other direction you can go is to stay in 3D, but allow arbitrary initial metrics. So in other words, we want to drop the assumption of positive Ricci curvature. Now, if you do that, then the problem becomes much harder because you can develop much more complicated singularities. And so the typical example is what Hamilton called a neck pinch singularity. So the idea here is, imagine you take a connected sum of 2 round spheres. So you take 2 round S3s and then you join them by a neck which looks like a small 2 sphere crossed with an interval. And so this is what I've tried to picture here. And then you take this as your initial metric and you evolve it by Ricci flow. Then what happens is that these big 3 spheres, they will shrink, but the little cylinder that connects the 2, this will shrink faster because it's smaller and has more curvature. And so then this neck joining these 2 3 spheres, this will pinch off before the 3 spheres have a chance to contract to points. And so then a short while later, you're going to get a picture similar to what I depicted on the slide, where the cylinder has collapsed but these 3 spheres, they're basically still there. And so then the curvature blows up along this in the cylindrical region, but it stays finite away from it. And so here, what makes this picture difficult is that the curvature doesn't go to infinity sort of uniformly everywhere, but it goes to infinity in some regions, but not in others. Another picture is you could have what's called a degenerate neck pinch. And here, that would not be modeled on a cylinder, but rather would be modeled on the brine soliton. Okay, so the understanding of these singularities, this was made possible by a series of breakthroughs by Perelman back in 2002. And let me just tell you about some of the essential ingredients that go into this. And so one of them is Perelman's non-collapsing theorem. So what Perelman proved is that any finite time singularity of Ricci flow has a certain non-collapsing property. So the definition is that if you have a solution to the Ricci flow, we say that it's kappa non-collapsed. If you get a lower bound for the volume of balls, whenever you have an upper bound on curvature. So loosely speaking, kappa non-collapsing means that curvature controls volume. And more precisely, if you have a ball of radius r, where the curvature is controlled by 1/r squared, which is the correct scaling. And so this r on the right-hand side, this is the same r on the left. Then the volume of that ball is bounded from below by a constant times r to the n. And so this constant, this is called the non-collapsing constant. So up to this point, this is just a definition. And in fact, the definition is implicit in Hamilton's work, but Perelman's great breakthrough, or one of many great breakthroughs in Perelman's work, is that he showed that its non-collapsing property, this is shared by any singularity model for the Ricci flow that models finite time singularities.
RM, capital R.
So n is the dimension, and R to exactly.
But M, when you're assuming the
Oh,
curvature.
so this is my notation for the Riemann tensor.
Okay.
So you take the full curvature tensor and measure its norm, and if that's bounded by 1/r squared, then you want a lower bound for volume. Yeah, so now if you have a solution that starts from any compact initial metric, and let's say it forms a singularity in finite time, then the solution itself is non-collapsed. And because this non-collapsing property is invariant under scaling, that means if you look at any blow-up limit, any singularity model, that will be non-collapsed as well. Now, this is significant for many reasons. One of them is that it rules out many singularity models that otherwise would conceivably be possible. So let's take a look at the list of examples that I showed you. So the shrinking spheres in dimension at least 2, they're non-collapsed. In the shrinking cylinders in 2D are collapsed, but they're non-collapsed in higher dimensions. The cigar soliton is collapsed, but the Bryant soliton in higher dimension is non-collapsed. So you can already see that this there's no way you can roll out shrinking spheres, shrinking cylinders, and the Bryant soliton. And in fact, all of these occur as singularity models. So there's a good reason why you cannot expect to roll them out. On the other hand, the shrinking cylinders in 2D cannot occur, and the cigar soliton is rolled out as well. And so in particular, this is one reason why when you try to prove the uniformization theorem in 2D, why you cannot get neck pinches, because a neck pinch would be an S1 cost with an interval, but then this cannot really happen because A, the S1 wouldn't pinch off because it has no curvature, but B, you can also see it because S1 cost with an interval is collapsed, and so this cannot occur. All right, so Perelman achieved a qualitative picture of what singularities in 3D Ricci flow look like. And so one of the central concepts in his theory is the concept of an ancient solution. Now, let me explain what an ancient solution is. So an ancient solution, this is a solution to Ricci flow that has a back history going back all the way to -infinity. So the intuition here is that ancient solutions to parabolic PDE, they're analogous to entire solutions of elliptic PDE. So like if you study, even in the simplest case, the linear Laplace equation, then like the Liouville theorem tells you that if you have an entire solution that has very special properties. And similarly in minimal surface theory, there's the Bernstein theorem that tells you that if you have an entire minimal graph, that has very special properties. And so in the Ricci flow, the analogous concept would be a solution that's complete in space, so that you can go all the way to infinity in space, and you can also go all the way back in time. And so these solutions, they often arise as singularity models. So the idea is basically, you would take, let's say we take some solution to the Ricci flow, starting from a compact manifold, and then we want to zoom in on a singularity, on a region where the curvature is very large. And so then we would dilate to make the curvature 1. But then if you dilate in space, you also have to dilate in time. And so then if before dilation, you had a certain finite time span, then after dilation, you get a very large time interval. And so then, assuming you can take a limit, then it's reasonable to expect that this will give you an ancient solution. Just as in the elliptic regime, if you do dilations and pass to a limit, you expect to get an entire solution. Okay, and so what Perelman proved is that if you take any solution to the Ricci flow on a compact free manifold, and if you have a singularity at some finite point in time, capital T, then near each point where the curvature is large, you can approximate a solution to any desired degree of accuracy by an ancient kappa solution. And by that, Perelman means an ancient solution, which is kappa non-collapsed and satisfies certain extra conditions. For example, it has positive curvature or negative curvature. So basically, this is the first part of Perelman's theory. So it tells you that singularities are modeled on ancient kappa solutions. So then if you understand what ancient kappa solutions look like, then that will tell you what singularities for the Ricci flow look like in 3D. Now, the second part of Perelman's theory is that he has a qualitative picture of what these ancient kappa solution look like. And so basically they look like either the cylinders, or they could be spheres, or they could look like a long tube with a neck attached with a cap attached on one side. So maybe let me draw a picture here. So you would have a tube that's half infinite going all the way to infinity, and then you have a kind of cap attached on one side. And here you have a tube which has the property going all the way to infinity, which has the property that every point lies on a neck. Now, this tubular region, this is quite well understood, but you know very little about the cap. So basically, you know its topology, and you know certain qualitative properties, and that's it. But this is sufficient for topological conclusions. So the proof of the Poincare conjecture, that only requires this qualitative picture, but you don't actually need to know what exactly the cap looks like. And the way Perelman did that is by extending the flow beyond singularities by a surgery procedure, and then he keeps going until the flow becomes extinct, and that's how he proved the Poincare conjecture. All right, now let me go back to the ancient kappa solutions. So they played a central role in this theory, and like we know that they serve as models for singularities, and Perelman had this beautiful qualitative picture that allowed him to prove Poincare. Now, in his paper, he made a conjecture. So he conjectured that apart from the shrinking cylinders and certain quotients, there's only one non-compact ancient kappa solution in 3D, namely the Bryant soliton. So basically the picture is, you expect the cylinders, you expect the spheres, but here let's focus on the non-compact case. And then you expect to get the Bryant soliton. And then there's one other non-round compact ancient solution, and you expect these are the only examples. Yeah, right. So in 2018, I proved that Perelman's conjecture is true, and that in the non-compact case, you really only get these two cases, either the Brine soliton or these exact cylinders. And so in particular, you have like a finite list of examples, and you know exactly what the geometry looks like from a quantitative point of view. Now, this result for Ricci flow, this classification result, this has a precursor in mean curvature flow, which I proved in a joint work with Kyung-Soo Choi in 2017. The two problems share some common features, like in the Ricci flow and the mean curvature case, but there are also some major differences. So Ricci flow is always the harder problem, and in mean curvature flow, you have more techniques that you can bring to bear than in Ricci flow. Okay, so let me tell you about some of the ingredients that go into the proof of the classification. So there are many technical steps, but let me just give you a high-level overview. So the proof involves 3 steps. So I first have to understand 2 special cases, and then these special cases help understand the general case. So the first special case is to look at self-similar solutions. So when I showed you the cigar soliton and the Brine soliton, these solutions had a special property that they move by diffeomorphisms under Ricci flow, so that the geometry, it gets reparametrized, but it doesn't change other than that. So the metric at time t is just a reparametrization of the metric at time 0. So now you can look at solutions with that property. And so there are ancient solutions, because since the geometry doesn't really change in time, you can go back to time all the way to -infinity, and you can go to +infinity, and the geometry doesn't really change. So in a certain sense, you can view them as fixed points of Ricci flow, modulo diffeomorphisms, modulo reparametrization. Now, restricting to that class of solutions, the self-similar ones, then that's a more restrictive class, and you have more techniques, and you can show that every kappa non-collapsed soliton in 3D has to be the Brine soliton. The idea being that you can understand the asymptotics at infinity, you can show that near infinity it's symmetric, and then the idea is to show that the whole solution is symmetric. All right, the second step is to look at general ancient solutions, not necessarily self-similar, but you make your life easier by requiring rotational symmetry. Now that's a huge simplification, because then instead of 3 space variables, we really only have 1 space variable, and instead of a system, we can reduce it to a single scalar equation. So you get just 1 scalar function, which depends on 1 space and 1 time variable. Now, the PDE is still quite complicated, and it's nonlinear and it's degenerate, but at least it's a scalar problem, 1 space variable. And by analyzing this PDE, one can show that every non-compact ancient kappa solution in 3D with rotational symmetry has to be the Brine soliton. Right, and this, of course, this is assuming that you don't have a cylinder. Right, so this is the second step, and then the third step is to look at a general case. So now we want to look at a non-compact ancient kappa solution, and we want to show that it's rotationally symmetric. And again here, let's assume that I have to assume that these cylinders are excluded. So let's assume we have a solution that's not a cylinder, and it's an ancient kappa solution, and I want to show it's rotationally symmetric, because if I can show that, then step 2 tells me it has to be the model solution, the Brine soliton. So how can you do that? Well, the idea is to leverage the classification of self-similar solutions. And so that there's a principle that Hamilton discovered in the 90s, that if you look at a general ancient solution, and if it has certain asymptotic properties which are satisfied here, then you can find some sequence of times going back to minus infinity, such that if you look at these snapshots in time, then at these times, the solution will look like a self-similar solution. And so now, because of step one, we know that the only self-similar solution that can occur is this Bryan soliton. And so then what it tells you is that there is some sequence of times, and they could be very far apart, where the solution looks like the Bryan soliton. And so in particular, the solution has a high degree of symmetry along some carefully chosen sequence of times going to negative infinity. But it's possible that along a different sequence, the solution could look totally different. So you only have this one particular sequence where you roughly know what the solution looks like. So now the argument is, we try to argue that as you go forward in time, starting from this time tk hat, if you go forward in time, the solution doesn't lose rotational symmetry. So at time tk hat, it's nearly rotationally symmetric. And then I want to argue that the degree of symmetry doesn't deteriorate too much, and you still retain this almost symmetry. And then, because you can go back farther and farther, then you can start with sort of initial data with better and better symmetry. And then if the symmetry is maintained, then you can show the whole solution is rotationally symmetric. So the proof of that the symmetry doesn't get worse, this is the heart of the matter. And well, the way you do it is you look at two different regimes. That's kind of this tube region. So by Perelman's work, we know that there's a tube region and a cap region. And in the tube region, you can show that if you're very close to a cylinder, then a linearized analysis will tell you that the symmetry gets better. And then on the cap, I can show that as long as it's reasonably close to the Bryan soliton, the symmetry also gets better. And in that way, you can set up a continuity argument to show symmetry. And another ingredient here is the classification of solutions with rotational symmetry. So that kind of help, because you understand these solutions that are symmetric, then you have a good understanding of solutions that are nearly symmetric. And then you can argue that if you're nearly symmetric, the symmetry gets better. So an interesting aspect is that understanding the rotationally symmetric solutions helps you prove that a general solution is rotationally symmetric. Anyway, so this is just an overview of the argument. Of course, there are many details that need to be made precise, but in any case, you can now combine the classification of ancient kappa solutions with Perelman's work, and then this leads to the following corollary. Suppose we start with a solution on a compact three manifold, and let's say we have a finite time singularity, then the high curvature regions, they can be approximated by just three basic models: the round sphere, or possibly a quotient, the round cylinder, and by round I mean the cross-section is round, and you could have a quotient of that as well, or the Bryan soliton. And these are the only possibilities. And you get any desired degree of accuracy by specifying a sufficiently high curvature level. So you have this so basically, the more accurate you want this picture to be, the higher you need to set a curvature threshold above which this result holds. And all these models, they are known to occur. So it's yeah. Maybe in the last couple of minutes, let me tell you about the compact case. So this is less relevant for singularity formation, because as you go into a singularity, typically you see a non-compact solution, but ancient solution, but these compact ancient solutions, they arise as kind of models for how you, for how the solution looks like post-surgery. And here, there's a companion theorem in the compact case, which says that you have basically two models, the shrinking spheres and their quotients, And then the second one, this is a special ancient solution with rotational symmetry, which was found by Perelman. And this one, you cannot write it down in closed form, but it's rotational symmetry. And there's a kind of qualitative picture of what it looks like. So Perelman's solution, it looks roughly like this. You take two prime solid lines. So you have one, and then we look at a second one on the other side, and then you kind of join these together. And then you get this some kind of oval shape. And there's an ancient cover solution that basically looks like such an oval, but we cannot write it down in closed form, but asymptotic expansions, and it's quite well understood. And so it turns out that this is the only non-round example in the compact case. And so then that gives you the classification both in the compact and non-compact case. All right, and with that, I'll stop. Thank you.
I had a few. All these things seem to be positively curved.
That's correct.
Where are the negative curved ones? What's happening to them?
That's an excellent point. So the negatively curved ones, they would, so if you start with a hyperbolic metric, it would exist forever and it would sort of inflate and the curvature would go to zero. And so these come in if you want to understand, if you don't have finite time extinction, then you would have to deal with those as well. Now, for a counterexample to the Poincare conjecture, we know that the flow would exist only for finite time and then become extinct. So that in that case, you don't have to deal with these. On a technical level, there's a famous estimate by Hamilton that tells you roughly that the curvature has a lower bound given by -1/t. And so then for large times, sort of the curvature gets pushed towards the negative curvature.
And in a similar way, the Thurston picture, chopping three manifolds into pieces, does this interact with that?
It does. So basically, what would happen is you would have these net pinches, and then the decomposition along where you cut along the tori, this would come into play for t going to infinity. And by now it's known that the surgeries stop at a finite point in time, and then you have a smooth flow. So so basically this picture comes into play in finite times when you have very large curvature.
So this might be a very naive question, but it's something I know a little bit about mean curvature flow. So it's very useful to make the notion, to relax the notion of a manifold, look at varifolds and associate a generalized notion to understand singularities. What happens after singularities? Is there a notion of Ricci curvature for such a sort of geometric measurement?
That's an excellent question. So there are a couple of attempts to define weak notions of Ricci curvature. I mean, one is through techniques from optimal transport. You can make sense of manifolds with lower Ricci curvature bounds in terms of optimal transport problems and certain concavity properties along Wasserstein geodesics. Now that's in the elliptic world where you don't evolve anything just for lower Ricci bounds. Then there's a very interesting piece of work by McCann and Topping, where they don't look at Ricci flow, but they replace Ricci flow by an inequality. So ddTG would be compared to minus twice the Ricci curvature, but you only impose an inequality. And it turns out that, I mean, a number of interesting properties hold if you just assume an inequality, and that admits a weak formulation via optimal transport. And then there's a third approach due to, I believe, Kleiner and Lott, where in 3D, they use these surgically modified flows, and then they send the surgery parameters to infinity to get a kind of weak flow. But that last approach, so that gives you more in that it would not just give you sort of a super Ricci flow with an inequality, but it would really give you a weak solution of Ricci flow, but it uses the Perelman machinery, and it relies on the fact that you have these surgically modified flows.
So you mentioned the ancient solutions come back to mentioned but like much more with the higher probably some other interesting.
Yes, so 4D and higher dimensions are quite well understood if you assume a positivity condition on curvature. And so there are various conditions you can assume. You can assume stronger conditions that give you convergence to round metrics. And there's some assumptions where you can say that an ancient solution with such properties is round already, but then you can weaken it. And there's a natural condition which is called positive isotropic curvature. And in a way, if you impose this condition in dimension at least 4, that gives you a picture that's fairly analogous to the 3D picture with no curvature assumption. So that's, I think, a useful analogy. Now, if you go beyond that and you make no assumptions whatsoever, then it's wide open.
So if you don't import collapsing, do you get other solid ones?
Yes, so then you get these flying wing solutions. So then you get other solitons. That's a good question. I have to check. I mean, they might come into play in terms of infinite time singularities. Is when you might get collapsed models.
These classification theorems, is it understood if you have, say, like if you are given an example, do you know which model? Are you able to tell which model it's?
You mean for a specific initial metric? Well, you can sometimes roll some of them out. I mean, so for example, let's go back to the classification of singularities. I mean, if you start with positive Ricci, then basically you can, by Hamilton's form, you only get the first one, and you don't get a second and third. But in general, I think it's hard to predict what you can get. I mean, for the dumbbell-shaped matrix, you know that like you can produce S2 cross R as a singularity model. I think Ryan Soliton, that takes more effort, like to construct an example where that actually happens. So I mean, this is not a precise statement, but presumably the Ryan Soliton is non-generic. So I think typically you would get the neck pinches by the Ryan Soliton. At least it takes more work to construct an example where it arises.
I think this isn't perfectly precise, but so with this result that's on the screen, is there a sense in which, so we have this locally, this is well approximated by these two cases. Is there a sense in which that degree of accuracy in the approximation is uniform, or like about, or maybe it can't be in general?
That's an excellent point, and it is not, and this is a feature of the problem, because the idea is any singular time. I mean, the simplest case is you would expect maybe there's only one singularity that happens, but in general, you could have many regions where singularities happen, and they could happen at different scales. And so let me try to give you a more precise statement. So let's say I have one point where the curvature is large. So let's say I have a point P in N, and let's say the scalar curvature at that point, let's say it's 1 over R squared, and R is small. So this P lies in a high curvature region. So then basically what is the Saltatsu is that you can look at a ball of radius, let's say 1 over epsilon times R centered at P, and you can, let's say you have a point maybe T0 in time, which is maybe close to capital T, and then you would look at a region where you go out in space to distance R, and a large multiple of R, and you go in time back from T0 to T0 minus R squared maybe over epsilon. So in time, you can go back a large multiple of r squared, and in space, you can go out a large multiple of r. And then you know that in this region, the solution looks like one. So that this is epsilon close to one of the models. Right, so in that sense, it's local, but you can, if you rescale the curvature to be one, you can go out a large but finite distance. And you can make this epsilon as small as you like, but then the price you pay is you have to make r, sort of, this r has to be extremely small then. So you have to look at points with extremely high curvature for that to be valid. But then you could have other points, sort of where you have another model at a different point in space. So the high curvature region would be kind of a gluing of these things. And so Perelman calls these canonical neighborhoods. And then the theorem is basically that the set where the curvature is large is covered by canonical neighborhoods.
Excuse me, may I ask some questions? I'm sorry, I'm online. Excuse. My question is like for the notion of like non-collapse. May I assume it is somehow we are avoiding the coin. Like is that the same thing? Like the non-collapse means we don't have any.
So maybe it sounds great. No, nothing.
We can go large together.
That would be wonderful. What's a good time for you?
Because I book something. Then if we can, I can hold something and we'll email you.
That's wonderful.
Yeah, that's what you do.
Wonderful. Looking forward to it. Thanks a lot. Nice to meet you.
Wonderful.
Well, I mean, you're not, you're used to this.
Thanks a lot. Yeah, it's a lot of questions. Hello. That's right. So what happens? It was quite peaceful for a long time.
Yeah.
But then the students opened the building.
Yeah.
And then they had that. They moved and
Right.
the campus.
Yeah.
For us. So,
I guess exams are online.
Yes, let me see here. So in 2D, the negatively curved case is easier. So I'm pretty sure the negatively curved ones, so ancient solutions on the surface of higher G's. Let's see here.
Well, they can first officially for.
Yeah, I think my guess is they don't exist because if you have a, let's say if you have a positive curvature, let's say you have a metal so capital T. So okay, G of for T negative.